recovering waste heat is certainly a way to improve overall power plant or even manufacturing plant effectiveness. One can argue that for an electric power plant, uh, recovering waste heat uh, might not be considered improving the thermal efficiency of the cycle, but do recognize that certainly when you recover waste energy and utilize it to reduce your operating costs, you're certainly improving the plant's effectiveness. And so it's certainly a worthy topic to discuss here for Chapter 8. So the more I thought about this particular topic, in which we're recovering waste heat from exhaust gas, the way we model thermal efficiency would be the amount of heat that's going into the working fluid, into the H2O. And so you can probably see that the idea of waste heat is more of a measure of the furnace operation rather than the H2O circulating through the thermodynamic cycle. And so I have to be a little careful about talking about improving thermal efficiency of the cycle when we're trying to recover waste heat. So with those disclaimers, let's go ahead and see how an economizer works. Well, let's see. So, of course, you've memorized now the basic elements of the working fluid, H2O, phase change substance, and you know what those four components are. But let's look at adding a piece of equipment where we will recover waste energy outside this thermodynamic cycle, but the energy we recover, we're going to be adding to the working fluid of the cycle. And so what are we trying to do here? Well, we're trying to improve the thermal efficiency of the plant. And I guess we could consider in some ways we could say, yeah, we're going to improve the thermal efficiency of the plant because what we're going to do is we're going to take the feed water that's up to boiler pressure and we're going to recover waste heat from the exhaust stream and we're going to add it. And so we're going to increase the temperature of the temperature, therefore the enthalpy of the compressed liquid going into the boiler. So I think we could argue that we are improving thermal efficiency of the cycle the more I think about it. Well, and this is called an economizer. So an economizer is a piece of equipment that recovers waste heat from exhaust gas and puts that heat into boiler feed water. And so this is what an economizer looks like. We've got a hot exhaust gas coming from the boiler furnace section, and it's in thermal communication with feed water coming from the feed water pump. So therefore, the feed water is being heated up some by reducing the temperature of the exhaust gas. So we are recovering. It's almost like free energy. We're recovering exhaust gas energy that otherwise would simply be sent to the atmosphere. And so here's a cross-sectional view, and we call this type of heat exchanger, the economizer, we call it cross-flow heat exchanger because you can see how the air is going vertically up, and you can sort of visualize that the feed water is kind of visually going side to side. Okay, so that would be a cross-flow heat exchanger. And where would this be located? Where would the economizer be located in your steam generating unit? Remember, ultimately, we got a thermodynamics class going on here. So here's our high temperature heat reservoir adding heat in this boiler equipment. And what we're doing is we're transferring heat from the hot exhaust products into the H2O. And so you can see that if we follow the exhaust products, we're coming down and then ultimately going out to the exhaust stack. And so the economizer it's outside of the furnace section, but it is still involved with the furnace itself. Okay, so I think you get the idea. Fuel and air coming in, exhaust gas coming out. And on the other side, feed water coming in. And for our basic Rankine cycle, it's coming in at state 4. Okay. Ultimately, it's coming out, going to the superheated steam, going to the steam turbine at state 1. So that shows you where we are relative to our basic Rankine cycle. Well, how would you sketch an economizer? This is the way I would sketch an economizer and write down some basics of continuity for that. I would show it as a shell and tube heat exchanger, even though we know we've got cross flow. I'd show that we've got, let's see, our feed water coming in at state 4, and then I'm going to label it 41 because we don't have that. I don't have that labeled on the Rankine cycle or TS. Okay. 41, it's going to be heated feed water going off to the boiler. Okay. On the exhaust gas side, we're coming in, and I just picked states 21 and 22 just sort of arbitrarily to show that our exhaust gas is coming in and it's cooling off. It's exchanging energy with the feed water coming out at state 22. Now, wow, how would you model exhaust gas? I'm getting off track a little bit. Think about, while we're going through these slides, how would you model exhaust gas? Phase change substance? I don't think so. I tend to I model exhaust gas as an ideal gas. That's what I do. All right. So, but let's look at the fundamentals. Continuity equation: m dot 4 equals m dot 41. That's your one inlet, one outlet, steady state, steady flow. On the exhaust gas side, same idea: steady state, steady flow. So m dot 21 is m dot 22. Both of these are operating at constant. There's no, for our model, we're really not dropping much, if any, pressure across 4 to 41. So the feed water pressure, it's not dropping significantly across this economizer. We say constant pressure process. Same idea for the exhaust gas. We're going to say that if we've designed our economizer well, we'll have only a slight pressure drop of exhaust gas pressure that's ultimately going to P atmosphere, right? So let's see, what else? No change in kinetic energy, no change in potential energy, steady state, steady flow. I think you have the idea. So that was our sketch. That's how we would draw a sketch if we had this problem out in the field. So some physical and second law limitations. Hopefully you're starting to look kind of familiar to you. Do you see that let's see, the temperature of the feed water going to the boiler is never going to get above the exhaust gas inlet temperature. No way. That's the statement of the second law. So T41 can never be bigger than T21. Okay. Another physical limitation is, as we're designing our system, recognize that you really can't extract so much energy from the exhaust gas that you're going to boil this water. It must continue to be in the compressed liquid phase. So that's something, as an engineer, you must check, because this exhaust gas is going to be coming in very hot, very hot. And so you want to be sure that the combination of mass flow rates is not resulting in boiling the water coming out of the economizer, but we must have compressed liquid going into the steam generator for a number of subtle reasons. Okay, and similarly, let's look at the exhaust gas out. Do you see that there's no way we can cool the exhaust gas down below T4? It can't get colder than T4. Okay, so that's a second law limitation. So what would our TS diagram look like? Now, so the TS diagram, remember, is only for H2O. TS diagram is only for the working fluid. It has nothing to do with the exhaust gas. So we're not going to visualize our exhaust gas anywhere on the TS diagram. So basically all we need to look at here is we're going into our, well, it says feed water heater. So shame on me, that would be a copy and paste error. That I should say into economizer and leaving economizer, going in at state 4, leaving at 41, and then going right into the boiler at that point. So this is where we're recovering energy from the exhaust gas. So you could think of an economizer as a feed water heater a little bit, but we still just call it an economizer because we're not using any extraction steam. We're recovering waste heat from the exhaust economizer. So now in our analysis, we're going to write the first law for our economizer. Should look familiar. So look at the repetition here. It's a heat exchanger. It's steady state, steady flow. We've got 2 inlets and 2 outlets. No changes in kinetic and potential energy. Let's see. We're going to consider that the economizer is fully insulated from its surroundings. The economizer is not lifting a weight, no shaft coming out. So the first law is going to say Q dot in, 0, minus W dot out, 0. So 0 equals the sum of the M dot leaving H leaving minus the sum of the M dot in H in. So we're getting some good practice with this first law business. So we'll look at our sketch. So do you see that we can simplify this down into M dot 4 times H41 minus H4? That's going to be the H2O side, the feed water side, plus the exhaust gas side, M dot 21 times H22 minus H21, out minus in. Okay. What else can we do? What else can we do to simplify to get to some numerical results? Well, the chances are good that as an engineer, you're going to know the mass flow rate of your feed water. And due to some calculations, you're going to know the mass flow rate of your exhaust gas. You can do some calculation to determine how much fuel and air do I need to produce so many pounds per hour of steam. That's part of your job, right? So you're going to know M dot 21. Well, I'm going to treat exhaust gas as an ideal gas with constant specific heat. And look, that generally there is so much. I'm going to treat it probably like maybe a gaseous mixture. I might even treat it as air, because depending on the amount of excess air that's going on, that's being used in your combustion process. So somehow by hook or crook, I'm going to find a value for C sub P for the exhaust gas. So I may look up Cp for air times delta T, T21 minus T22 to get my signs right, okay? And so those temperatures will be known, and that's going to enable you to solve for H41. That H41, in other words, if you know your M dots, both your M dots, you've looked up C sub P, and you know how much energy you're trying to extract or cool down your exhaust gas to, that's what's going to enable you to calculate H41. You're down to one equation or one unknown, depending on your given problem situation. I do not expect that you're going to have a homework problem associated with an economizer. However, in ME 3204 heat transfer, you may well be exposed to or have an opportunity to analyze an economizer transferring heat from hot exhaust gas into boiler feed water. And so that's important. Let's see, what else did I need to mention? Solve for H41 and check for those physical limitations to be sure that you're not boiling the water at state 41. And then finally, as a familiar reminder, an economizer is simply, it's a basic heat exchanger in cross flow. And so if you're interested in learning a little more details about heat exchangers, I've got a video in Chapter 4, Part 10, and talking a little bit more about that. So there you go. Just for completeness, an example of how you might look at recovering energy, waste heat energy from hot exhaust gas, commonly done in the design phase of designing thermal systems.